JMO 2024 problem 4, let n greater than equal 3 be an integer. Rowan and Colin play a game on an n by n grid of squares where each square is colored either red or blue. Rowan is allowed to permute the rows of the grid and Colin is allowed to permute the columns. A grid coloring is orderly if, no matter how Rowan permutes the rows of the coloring, Colin can then permute the columns to restore the original grid coloring. Look, because pay attention, Rowan are permute rows, Colin columns, okay? No matter how Colin permutes the columns of the coloring, Rowan can then permute the rows to restore original grid coloring. In terms of n, how many orderly colorings are there? It says n at least 3, but let's also check. I want to use a small example, okay? And by small example, I want to find the idea. And I want to see which tables are good and then prove it. We solved many problems of JMO and AMO by small examples. So let's consider a small example on n1. For n1, first one cannot permute, second one cannot permute. Because we have only one row and one column, so all of them are good because you can restore the original grid because it doesn't change. So the answer is 2. If n is 2, let's check this. If all of them have same color, for example, A, then it's good because again it doesn't change. So two cases here. Here it was 2 for n1 because all of them black or all of them white. 3 of them black, for example, let's consider 3 of them black. Without loss of generality, suppose it is this. If R permutes these two rows, then we have what? This. And here we had 2 blacks, 1 black. Now here we have 1 black, 2 blacks. If we want to permute columns, we can see that this one still will be 2 if you permute columns. So we cannot reach this one, okay? By permuting columns, number of blacks in this row doesn't change. Okay, so we can say what? This one is not good, 0. If we consider two blacks can be like this or like this one. One black is similar to 3 blacks, so it's okay. And here we consider, for example, 4 blacks or 4 whites. Both of them are same and they were good. So for this one, again, if you permute rows here and if you permute columns, you cannot reach original diagram. Okay, so this one again, 0. This one, for example, if you permute rows, it will be what? It will be like this. If you permute columns, it will be, sorry. If you permute rows, it will be this one. If you permute columns, it would be this one. And obviously, you can first permute columns. You can reach original diagram by permuting rows after that. So we have 2 cases, 2 blacks like this or 2 blacks like this. So how many good cases? 2 plus 2, 4 good cases. Okay, so for n1, the answer is 2. For n2, the answer is 4. Okay? And the problem says start from n3. In n3, we can find some good results. So for n3, let's try an example, okay, to see it's good or not. Because we cannot check all cases in the beginning. For example, this. Suppose we, for example, permute these 2 rows. Then it would be what? This one, this one, this one. By permuting columns, you cannot reach original diagram. Why? Because if you permute columns, again here we have two blacks, here one black, but here we have two blacks and one black, but it doesn't change. So we understand that we should pay attention to number of blacks in each row and number of blacks in each column. So suppose, for example, we consider here we have R1, R2, R3 blacks, C1, C2, C3 blacks. And for example, suppose we permute R1 and R2 as an example. So this one will be R1, R2, R3. When you permute these two rows, number of blacks in each column won't change because in each column these two will be switched and this one won't change. So number of blacks again will be C1, C2, C3. And now, if you want to permute columns, number of blacks in rows won't change. Okay, so we can say that R1 should be equal to R2 if you want to reach this one again by permuting columns. Okay, because if you permute this, these things won't change. So R1 should be equal to R2 if you want to reach this. So R1 should be equal to R2. Similarly, R1 should be equal to R2, R3. And similarly, again, we can say C1, C2, C3. So because we know now, sum of R1, R2, R3 will be number of blacks. R1 plus R2 plus R3, number of blacks, is equal to C1 plus C2 plus C3. Okay? It is equal to number of blacks with double counting. Okay, we can call this idea, it's important. Changing viewing angle, we can call it, or professional name, double counting. In AMC also, I saw a problem with this idea. So we can conclude what here? We can say, okay, R1, R2, R3, because they are equal, is 3R1 here, it is 3 C1, so R1 is equal to C1, so all of them are equal. R1 is equal to R2 is equal to R3 is equal to C1 is equal to C2 is equal to C3. Exactly, with the same approach, you can generalize it for n, general n, that number of blacks in each row should be equal to each other and also equal to number of blacks in each column and row. And now, we should consider x is what? Okay, x can be what? Number of blacks can be 0, 1, 2, 3. Okay, so x can be 0 or 1 or 2 or 3. And 0 and 3 are similar. So let's check one of them only. 1 and 2 also are similar because black and white problem is symmetric with respect to black and white. So let's check first x0. It's good because if you permute rows, the table doesn't change, and also for columns, so we have one good table. For 3 also we have one good table. Then now let's check x1. If x1 in each row and each column we have one black. Without loss of generality, consider it is this because this, and we know we have 3 factorial of this type, okay? All of them are similar because the blacks should be in different rows and different columns because x is 1. And each row and each column we have exactly one black. Now, suppose, for example, we permute column rows, okay? For example, it is 1, 2, 3. If we permute, for example, you say, okay, 1, 2, 3. So 1 here, it's this one, 2, 3. Then it's not important that our permutation is what? When we want to permute column, I say, okay, in which row we have a, let me tell you, you should pay attention when you want to permute column. You should pay attention in first row, our black is what? So you should move it to this. In second row, our black is what? You should move it to this. In third row, our black is what? You should move it to this. Okay? And then it would be a permutation. Why? Because you say what? You say third column should go to first column. First column should go to what? Second column. Second column should go to what? Third column. For n, as you can see, for each number, we have one out degree, one in degree always. Why? Because we know that in this column, third column, want to go to what? We have only one black in third column, so it is then it will be it has one out degree, and only one black should go to third column because we want to reach these. We have only one black in third column, so it has only one in degree. And because we have one in degree and one out degree, then it creates a permutation. You can say, okay, 3 goes to 1, 1 goes to 2, 2 goes to 3. And in graph, we can consider a permutation graph. I solved Sumac problem with this idea. Sumac problem. I will tell you at the end the problem was what. And when we have a graph and in degree and out degree of in degree means what? Input here, it's 1. Out degree is what? 1. So if you have a permutation graph and in degree and out degree of each vertex is 1, then you can conclude it is union of disjoint directed cycles, and then it is exactly, we have a one-to-one correspondence to a permutation. Okay, so we have these things. And now we can see, okay, so how many good graphs are there? 3 factorial. For x2, how many good graphs are there? Similarly, because when we have 2 blacks, we have 1 white. Okay, the problem is symmetric with respect to white and black, so we can say 3 factorial. So the answer for this part is what? 2 times 3 factorial plus 2 times 1. 2 times 3 factorial plus 2 times 1. Now let's write it. n3, 2 times 3 factorial plus 2 times 1. But is it 2 times 2 factorial plus 1? No. Plus 2? No. Maybe the reason that it says n at least 3 is this. So let's check n4. Okay, and we want to see for n4 what happens by the thing we reached here. So in this case, we want to consider first again x0 to x4. But we know again x0 and 4 are similar. And we should check x0, x1 and x2. Okay, these 3 cases. 3 is similar to 1, 4 is similar to 0. Okay, so x0 is good. So for x0 and 4, we have 1 case for each of them, so it would be 2 cases. Now, let's consider x is 1. Again, exactly by the same approach we did here for x1, it would be good, but because we have x1 and 3, it will be what? 4 factorial. Because for 1 in each row and each column, we have 1. So in first row, you select 4, for example, this. Then you select, okay, for next one, we cannot select this. So 3 cases are left, 3. Then here you cannot select this because in each column also we have 1 black. So you have 2 cases, this one and last one, this. Okay, 4 factorial for this one, 4 factorial for this one, 2 times 4 factorial. Now let's check x2, okay? And here, by considering x2, we can understand that can we have x except 0, n, and 1, and n minus 1? Now, in each row and each columns, we have exactly 2 blacks. In first row, without loss of generality, suppose first 2 cells are black. Now, because we know that in this column, we have 2 blacks because x is 2. Without loss of generality, suppose next black is here. But for next black in this row, it can be here or here. Okay, these 2 are similar, so we can consider one of them. So let's consider these 2 cases. This black, this black, this one is black, or this one is black. This one is black. Then for this one, because we know in these 2 rows, in first 2 rows and first 2 columns and first 2 rows, we have 2 blacks, so other blacks are exactly here. It would be unique. And what about this case? We know that in this column, we have 2 blacks. One of them is this, one of them, one of these 2. By symmetric, you can consider this one. Then in this row, we have 2 blacks. This column, we can't have black here. We can't have black here because 2. We can't have black here. So if we consider the black here, then for this row, we have problem because we should have 2 blacks. Or we can say for this row, we should have 2 blacks, this one and this one. And then for this row, because this column again has 2 blacks, so the only cell that is left is this. okay? Because if we place in any other cell, then we have more than 2 blacks in one row or one column. So you should consider these two cases. And I want to reach contradiction for both of them. How? For this one, I permute these two rows and let's see what happens. If we permute these two rows, then we have, let me write it with ink. These two are black, these two, and these two. Okay. Now, because if you want to go back to this one, so because of first row, we can only permute columns. We should move these two rows to this part, okay? Because of these two blacks. They are here, we should move them here. Then as you can see, then this part goes to this part, and then here we have in fourth row we have problem. If you want to correct first row, then in fourth row we have problem. So it is not good. Now, for next one, here they are consecutive blacks. In this row, they are not consecutive. So if we move them, then we cannot reach a good table. Why? Because it would be what? This one, 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 this one. So if you want to permute columns, these two can, let me tell you, if we make these two things adjacent, let's see what happens. So here we can reach contradiction. How? Because here it is white. If you want to go back to this part, we should move these to one of these two cells, okay? This column. Then what happens? This black also goes here, okay? And we know here we don't have any black. So that's a contradiction. So we should move these to one of these two columns, then this one also moves one of these two cells. But here it should be white. Both of them should be white. And that's a contradiction. Again, it's not good. So again, x1 and 2 are good. So 2 times 4 factorial, 2. It would be what? 2 times 4 factorial plus 2 times 1. And we can guess for n, our answer is what? Can you guess? 2 times n factorial plus 2 times 1. Let's prove this. Now if we work on general n, okay, now let's consider n by n. Again, obviously for x0 and n, it would be good because the table doesn't change. So 2 cases. And now I want to consider x1, again without loss of generality, because in each row and each column we can consider one row. With same approach like this, you have one input, one output, you can consider permutation graph and one-to-one correspondence to a graph. So for x1 and n minus 1, each of them n factorial cases. Now I want to reject x2 and then generalize it for xr. So we want to consider x is from 3 to n minus 2, okay? So let's check, for example, here. Oh, sorry. From 1 to n minus 2. So let's show this from 2 to n minus 2. We want to say all of them are bad. So here, if we consider we have x blacks in each row and each column, and x is between 2 and n minus 2, we can say what? I can permute rows, let me write R, such that, for example, in first column, all x blacks are consecutive like this. Then we should be able to permute columns to reach our original table. Because when you move columns, then you should move this column to other column. It means that in our original table, so suppose our original table was this, we reached this one, and we want to reach our original table here by permuting rows, and we reach this, and we want to permute columns to reach our original table. Because when we permute our column, this column, for example, goes to another column. But we know that we have x consecutive blacks in the beginning. Okay, first x cells are black. So it means that in our original table, we had a column that first X cells are black. Okay, like this, you can do it for any other. Let me erase this. For example, suppose we have X is 4, for example. I consider this one, I permute to reach this one, and this one. And when we permute columns, we should move this column completely. So again, we can conclude we have a column that has this black, these two blacks, this black. So like this, because we can place these X blacks in any of the cells in first column, so we can create how many columns for first column, how many blacks, and choose X. And we know for each of them, we should have one column in our original table that is equal to exactly that. So it is less than or equal n because we have n column. Okay. So, and we can, like this one, we can create, we can change first column to any of the cases and choose X. And so in our original table, we should have all of them. So n choose X is less than or equal n. If you had question about any part of the solution, or wanted to learn other ideas, feel free, as I said before, to send message to my WhatsApp number in the description. So now I want to prove it cannot be correct for x2 to n minus 2. How? I know n choose x is n factorial, x factorial, n minus x factorial. And then I can say, okay, it's n minus 1, n minus 2, 2 what? N minus x plus 1, if we cancel with n minus x factorial over x factorial, let's not equal n. Now we can say n times n minus 1, n minus 2, 2, n minus x plus 1, less than or equal n times x minus 1 times 2. Here, how many numbers are there? This last one minus first one plus 1, x numbers. Here, how many numbers are there? We can ignore 1, so x minus 1 plus this x numbers. This less than or equal this. We can cancel n from both sides. And we know that n minus 1, because we have x minus 1 numbers, consecutive numbers, x minus 1 numbers, because it is less than or equal this, so greatest one should be less than or equal this. So n minus 1 should be less than or equal x. And we can conclude x is at least 2, okay? Because you can consider x, because we said here, we should consider only x at least 2 and this. So this one, because the beginning number is 2, x is greater than or equal to, so n minus 1 is less than or equal x minus x. So, but that's a contradiction because we said that x is less than or equal n minus 2. Maybe you say, okay, for x1 0, what about this case, for example? This one should be correct. When x is 1 or 0, it's not x to 2 because we considered x to 2 means x is at least 2. Okay, so we reached contradiction for x between 2 and n minus 2. And it was the proof for this problem. Again, we solved this problem by considering a small example because it was related to graph permutation graph. Let me tell you, the SUMIC problem that can be solved with similar idea. Okay, Stanford University Mathematics Camp, SUMIC 2022. Summer camp for Stanford, problem 4. Again, you can solve it with permutation graph. You can do it as homework 1. If you want to solve more similar problems and want to learn important background ideas, as I said before, feel free to send message to my WhatsApp number in the description.